Hi, welcome to Interval Zero. We're here today to review the samples that come along with the RTX64 product. RTX64 SDK includes 19 samples. They come with full source code, Visual Studio project files. You can be up and running with one in a matter of a minute. These samples are delivered as a good reference for you to show the API set that's included with RTX64 and to give you a good quick start for your application. So you can use one sample, might get you through what your applications do. You might need 2 or 3 put together into your application to get you up and running quickly. The samples that we're going to cover today, they kind of fall into a few categories. The first one is communicating with Windows. When you have a real-time process, it's going to probably need to pass data to a non-real-time process, either for a GUI or a database, and it may have to go 2 ways. So we have 2 samples, the Windows RTX64 using STL. It demonstrates that, as well as the RTK IPC. And the RTK is actually a kernel program, a Windows kernel program, talking and signaling a real-time process. The next category is communicating with devices. So, quite often our customers will have to, use a PCI card or PCI Express card. And as soon as you do that, then you have to go out and figure out where that board is and what memory addresses you need to talk to. We have 2 samples that actually cover that. We'll show SCAN bus. And then once you get further along in your application, typically you want to see how it performs. See what kind of latencies your timers have, see what kind of determinism your processes have. So we'll review the SRTM sample. And the last one is the Ethernet Layer 2 filter drivers. RTX64 has a full TCP/IP stack and several Ethernet drivers, NIC drivers. So in between those 2, you can install this Ethernet filter. That will allow you to filter, which means you can drop or let pass or modify Layer 2 Ethernet packets. The first sample we can take a look at is the Windows RTX 64 using STL. We created this sample for 2 reasons. One was to show how to use the C++ standard template libraries. And the second was to show how to share data between 2 processes. And the 2 processes we were showing, one runs in Windows, and we call it the winproducer.exe, and the other runs in our real-time subsystem, and it's the rtconsumer.rtss. So to share data, we need to also signal each other to say when we've consumed that data or when there's new data. So with that, we actually used RT-pulse event as our IPC mechanism, and when one of the processes gets a notification, he can then, the RT wait for single objects notified, he moves on to do what he should do, which is in the producer side to give more data. He copies that data to the shared memory area. It's a single area in memory that both processes can look at. And then when the consumer gets it, he can signal the producer saying, okay, I've consumed that data, you can send more. So they can ping pong back and forth like that and pass data. The next sample is the RTK IPC. This one does a lot the same as the previous sample to demonstrate sharing data between 2 processes. But in here, the Windows process is actually a kernel driver. The RTK IPC driver.sys runs in the Windows kernel space, and it appears to Windows as a normal Windows driver. And the real-time process is the RTK RTSS app, and they're passing data back and forth, just like the previous example, but they need to do a bit more to do that because it's a kernel driver. So the first API is the RTK RTSS attach and detach function, and that is required because the one process is running in the Windows kernel. And in this in this example we show some of the other methods of IPC mechanisms. One are the mutexes to protect the memory, and semaphores to do the signaling. So in much the same way, they both use a wait for single object, and they can use semaphores or events to do the signaling. And the next sample is the SRTM sample, and that's a system response time measurement sample. And basically, we call it an RTAPI, so it's a real-time API timer latency measurement tool. So with this sample, you can take the code, because you get the full source code, and you can modify it and put it into your own application. And what it'll give you is you'll be able to determine how fast your system's running, or what kind of latencies you're getting when the system's under load. So you can try and load up the system, either I/O, accessing hardware, or just Windows processing, and you probably do both, and see how your system responds. And you can do that just with the sample. So you can run the sample, stress the system, and demonstrate what kind of latencies you'll see with RTX on your hardware. The APIs that are referenced are creating timers, because that's the context switch, and running those timers. You enable port I/O so that you can read and write actually to the legacy Windows I/O ports, and that's in there so that you can actually enable the system timer and actually hear the any differences in excessive latencies. You'll be able to hear them, because by default it sets a 1 kilohertz timer, which translates into the half that for the frequency you hear, and then any latency will appear as clicks. So you can actually hear it without just relying on the histogram that it ends up with. And this one, we can actually take a step-by-step look at how to build it, use it, and see the results. Here is the directory that the samples come in. So the SDK normally installs under the program files directory, interval 0, RTX SDK, the current 1.1 directory, and then the samples, and then under samples are all of our samples, the 19 of them. And this one is the SRTM, and you can see that we have Visual Studio 2010 and 2012 project files and solution files, but right now I'm using the 2010 solution file. So I open him up, and I can see my project here. So it'll build right out of the gate. We should see that. It's the SRTM project, and you can build it two ways. So you can build it as an RTSS debugger release, and that means it's going to be a real-time application, or you can build it as a Windows application debugger release, and we'll show the results of both of those. So as you can imagine, the Windows build should show higher latencies. So when we build these, they fall into the directory underneath those projects, and you can see the two directories that are built for the two different types. It's the Windows debug and the RTSS program. And then once we run this this application, it's going to output to the RTX server console window. Normally a command line would a non-real-time command line would output to your console window, your command window, but your real-time processes output printfs and to what we call the RTX server console. So you can see the results of this. This ran for 15 seconds on a 100 microsecond timer period, and you can see that a majority of those, 130,000 out of 150,000 context switches, were under a microsecond in latency. So that's pretty good results. This was on my laptop, so at first I wasn't sure how it was going to run, but it ran pretty good. The worst case was under 4 microseconds latency. We had one occurrence of that in a context switch across that 15 seconds. So now if we run the same, the Windows version of it, we can see that's in the debug directory. There's the .exe file. We run him, and he outputs to the command window, and it output a larger histogram because there was a greater variance in context switch, in latencies for the context switch. And you can see at best Windows had the fastest it could do a context switch was took more than 29 microseconds. The worst case was above 264 microseconds, and that's without Windows under load. So if you put Windows under load, you would expect to see higher numbers. If you put just Windows under load with the RTX version, the real-time version, you would not expect to see a higher latency because the Windows won't preempt the real-time subsystem. The next sample is the CAN bus example. So this is a good example because most of our customers will want to talk to a PCI Express board or some type of hardware, and to do that, those boards are plug and play. You'll need to go through and scan the PCI bus and find out which board is yours. So this uses the API RT get bus data by offset, and I'll explain what that is in the next few slides, because we'll step through this one as well. And once we do that, the CAN bus doesn't show exactly how to attach to it. So there's another sample called the Intel Pro E 1000, which we won't go through because it's a bit more complicated. But in that example, you can see the RT attach interrupt and the RT map memory call that you would use with data you'll get back from the CAN bus. So this is so the only API reference that's truly notable in the CAN bus is the RT get bus data by offset. And stepping through this, I brought you right into the Dev Studio directory, and you can build this one for debugging for Windows and RTX as well. It doesn't really matter since it's not doing any real-time processing. It's just scanning the PCI bus. And so when we run it, I ran the one the RTSS version, which outputs to the RTX server window, and it actually pumped out a lot of information. So this scrolled quite a bit, and I scrolled it back up to find a device that was interesting. So this was how the get bus data by offset goes through it. It goes through the bus number, device number, and function number, and goes through every one that's possible to find a matching, one, that the device exists, and then two, what you would do is find a matching device. You would use your vendor ID and your device ID, which would be unique for your particular card. The vendor here is 8086, that's Intel, and the device ID is the 1E3A. I believe that's an Intel NIC. So once we know what our device is, we find that, we then look at its base address. So we can get this base address, that's a physical address, map that to our virtual address space, and now we can talk to the board, the registers on the board. And then we also need to know the interrupt line. So we can use this value here to call the RT attach interrupt and actually respond to interrupts from this board. So this example will get you up and running quite quickly in talking to a PCI board. This is our final sample we want to review. It's the RT Ethernet filter. With RTX and the TCP/IP stack that's supplied with RTX 64, you can insert a filter driver in between the TCP/IP stack and the NIC driver. And in this sample, I'm using the RT IGB NIC driver, which is supplied with RTX 64, and the sample will actually insert itself in between the stack and that NIC driver. So in this way, the sample gets called when there's a packet transmitted or received, and in that way we get a pointer to the frame, and we can inspect the packet, we can modify the packet, we can also inject packets or drop packets, both in the transmit and receive direction. To do this, we get called when the stack is transmitting a packet, and it calls the RTND transmit filter. We get passed a pointer to the frame, and then on our return from that, we can instruct the stack to either to drop it, to not send it to the NIC, or to pass it along to the NIC. And the same goes for the receive RTND receive filter call, and we can also inject a packet. So we can allocate a frame, build it up ourselves, and it's a layer 2 packet, so we have to build up the MAC address and the ether type, and then we would call the RTND transmit call, and that would send it directly out the NIC. Packets we want to queue, we want to inject on the receive path, we will call the RTND queue receive frame. So this is great for it's a great example for doing layer 2 communication. It's similar to the Linux raw sockets, and you would use this for something like building an EtherCAT master. So you could go out and talk layer 2 communication. So any of the applications or any of the protocols that are fully layer 2 communications, this is an excellent example to show you how to build an application to do that. So there you have it. There's 5 of the 19 samples. I encourage you to go look at the remaining samples. They're documented in the RTX 64 help file, and as well as online. So you can just go online and look at the sample set and read the brief overviews that's covered in the documentation. You might find something that's more unique to your application than the 5 we covered here. And again, I encourage you to go through them and try them. If you're new to RTX and you want to jumpstart your application development, try the samples first. They may not be an exact match, but we found that our new customers that have used the samples to get going have moved a lot faster. We've had customers that didn't truly know that some of the samples existed, and so that's why we did this video. And so hopefully this gets your application up and running faster. And once again, thanks for watching.